So I got two really good questions during the break, so I'm going to just answer those questions. Well, you might be wondering why we are first growing a bushy tree and then pruning it back using two different algorithms while we can just grow a smaller tree to begin with. So this idea of tuning, the number of splits is also valid. It allows us to just grow a smaller tree to begin with. But there is some benefit to the more complicated idea of growing a bushy tree and then pruning it back. So when we use those two algorithms, first growing the tree using that process and then pruning it back to a subtree using this process, the advantage is that eventually we get a better tree compared to that strategy of tuning D. The reason is that we're solving these problems using some greedy algorithm. In particular, the tree growing algorithm is greedy, meaning that we are sort of myopic. We only see one step ahead of the process. So whenever we're considering a split, we only see how good the possible splits in that step are. And there could be situations where we are considering some split that doesn't have an immediate some considerable improvement immediately, but could lead to some substantial improvement in later steps. And with this second strategy, we want to make sure that we take advantage of those sort of improvements despite our greedy and myopic approach. So there could be situations where we are considering some split that only has a relatively small improvement in the loss function. But if we have that split, in the next step, we can have another split because of the split we decided on. And the second split has some substantial improvement for our loss function. So with this idea of letting the tree grow as large as needed, we're potentially including situations like that where we're not restricting ourselves to just doing, to just using splits that are immediately, that lead to some immediate and substantial reduction of the cost function. We also do some splits which are not that exciting because our stopping criterion is more relaxed. We don't have a limitation on D. So we have those splits which are not great immediately, but those are the splits that kind of take us to another space where we have some useful split later on. So that was one question. And the second question is about these spaces. The space of minimization between these problems are different because the second problem depends on the first problem. So in the first problem, pretty much the feasible space is all the possible ways that we can create a tree, which is some huge feasibility space. But we're solving this in a greedy base, which means that whenever we're considering a split, we're just optimizing over the possible splits we have at that point in the process. So we're optimizing over possible variables to split on, and then for each variable, possible values to split it based on. Then this is going to eventually lead to some bushy tree, and that bushy tree has a space of possible subtrees. So this S prime, which is the feasibility space for the second optimization, is the space of subtrees of the tree from step 1, from the tree growing process. That's why here the minimization is on a more restricted space. These subtrees are all the possible ways that we can prune that one tree we got from step 1. And there's a one-to-one correspondence between value of alpha and the subtree that we would get from step 2. That's why essentially step 2 gives us a collection of values of alpha and subtrees. For example, in step 2, we see that when alpha is 1%, there is some subtree which is relatively large. When alpha is 0.1 or 10%, there's a smaller tree. There's a smaller subtree, right? And then we're going to use cross-validation to decide on the value of alpha after step 2. So with this more complicated process, we have cross-validation at the very end to decide what is the suitable value of alpha. And that tells us, based on the complexity of the problem, how small or how large our eventual subtree should be. And then when we have the value of alpha from cross-validation, we're going to just use the subtree that we got from step 2, which is associated to the tuned value of alpha. So this second strategy is much more complicated than cross-validating D directly. But eventually it gives us a better tree because it kind of acknowledges and resolves the issue of using a greedy optimization problem. I mean, it doesn't totally resolve the issue because still we have some greedy algorithm under the hood, but the kind of disadvantages of that greedy algorithm will be lower because of the way we use these two algorithms. Any questions? I feel like you have a question.
So how about growing? Which algorithm we use to grow the tree?
It's this algorithm. It's the so-called recursive binary splitting algorithm. So it's an algorithm where we start at the root of the tree, and we decide which variable to split on, and what would be the value of that variable to create some boundary. So essentially, in case of tuna and salmon, at the beginning of this algorithm, first we decide whether we should split on weight or length. And then we decide on the value of W1 or W2. So in the first step, we're kind of considering all these possible lines here, as well as all these possible lines here, and just pick one line that gives us the highest reduction in RSS, or highest reduction in Gini index, or highest reduction in cross entropy. Right? So between these possible lines and these possible lines, there would be one line that has the highest reduction in the loss function. We select that, and we split the data based on that. Then we're going to have two nodes. Then this recursive algorithm works on each of those nodes similarly. Now, there is this subproblem, which is already solved to optimality because Gini impurity is 0, and there's this subproblem. So one kind of subproblem is done. Then for this subproblem, the decision to be made is whether we do another split vertically or a split horizontally. And it turns out that the horizontal split here is what gives us the highest reduction in the loss function. So then we just do the split, which is the split in here. Yeah. And then based on our stopping criterion, we see that here we have 8, so we don't continue this. And yeah, for this one, again, if there is some stopping criterion that prevents us from splitting this, we stop. Otherwise, this thing would continue. But also, we can have like a limit on how close to 0 is good enough for us. Because here, for region R2, the Gini impurity is really close to 0. It's really small. So let's say if there are 99 squares and 1 cross, it would be it would be this value, which is very close to 0. Any other questions? All right, if there are no questions, we can now move on to more advanced tree-based models. So the issue so far was that eventually when we do all of these things, there's a kind of natural limitation to what a decision tree can do, because they are highly interpretable, but in terms of accuracy, if we have kind of like nonlinearity in our problem, the way that we're doing these splits, eventually there's a limitation to it. The limitation is just because we are bounded to get these sort of boxy regions, which are so unnatural. So regardless of how much effort we put into a decision tree, it is eventually a decision tree with boxy regions. So what we're going to do is use ideas for aggregating result of multiple trees. And there are essentially 3 ways that we can aggregate result of trees. First idea is bagging, which gives us a bagged tree. Second idea is random forest. And the third idea is boosting, which gives us a boosted tree. So first, let's discuss bagging. So the idea of bagging is very interesting. It involves bootstrap aggregation. So it is some aggregation of predictions of a tree, and those trees are grown on bootstrap samples of the data set, bootstrap samples of the training data set. So the idea is this. When we have some Z1 all the way to Zn as IID variables, independent and identically distributed variables, with a mean of mu and a variance of sigma squared, when we take these variables and calculate their mean, which is Z bar, is just sum of Zi over n. The average of n variables is going to have the same center, the same average, the same mean, but the variance will be divided by n. So this is just such a nice statistical trick that we can have. Whenever we aggregate something, we get a more accurate result. So the idea of bagging is that instead of making a prediction based on one decision tree, let's just create n decision trees and aggregate their predictions so that the variance of our predictions would be lower. So the one issue with the decision variable was, with the decision variable was that it would overfit. So in terms of bias variance, when we let it grow too freely, it will end up here, which was overfit. It was overfit because variance was very high. So this idea works here because this is about reducing variance. But the issue is that we don't have n training data sets. We only have one training data set. So this is our training data set. It has, let's say, n observations in it. What we can do is get Bootstrap samples from this. So here is a Bootstrap sample. Here is another Bootstrap sample. So this is Bootstrap sample number 1, Bootstrap sample number 2. This is just some other data set. Some of these observations are repeated once, some of them are repeated twice, some of them don't appear in a specific Bootstrap sample because we're sampling with replacement. And this is Bootstrap sample capital B. So in total, we get capital B Bootstrap samples from the training data set. Any questions so far? So now that we have these Bootstrap samples, for each of these, we're going to fit a decision tree. So this would be the decision tree from this one. Let's say this is a decision tree from this one. And these decision trees are different because these data sets are different. And let's say this is a decision tree for this one. Actually, we don't mind that these decision trees even overfit. It doesn't matter because even if they end up here, they end up in some high variance region, we're going to aggregate the result for our prediction, and the variance would be automatically reduced because of this nice statistical property. So this idea of bagging is very, very interesting because we're kind of resolving the issue of bias variance trade-off in a different way. Instead of saying, let's pick this region, we say, all right, let's stay in this high complexity region because complexity is also sometimes useful. Maybe our prediction is on some data set that requires complexity. The whole issue with decision trees was that they were too simple. For many tasks, they are just too simple to make a good prediction. That's why with bagging, we do something very unusual. We say, all right, let's stay in this overfit region, but get n different predictions in this region and aggregate them so that the variance of the prediction is reduced. So then if we want to use this model, which is a bagged tree, this is essentially a Bootstrap aggregated collection of trees. So now if you want to make a prediction, this tree maybe says tuna. This one says salmon. This one says tuna. And there are n predictions. If this is classification, we can take the majority vote between them. We can see from the capital B trees, which prediction is more common? Is it tuna or salmon? We just go with the more likely, more common prediction. In case of regression, we can take their average of the predictions, because this is some, in case of regression, this is going to be some y hat, some value of y hat, this is another value of y hat, and this is another value of y hat. This is y hat we get from model number 1, y hat from model or tree number 2, y hat from model capital B. Therefore, we get some average y hat, some average of y hats, which is sum of y hat I from 1 to capital B over B. So in both of these situations, we're kind of doing something like this. Any questions? Yeah.
So at the beginning, all of these are represented.
This is not really about trees. This was just an idea to remind you that the average of n variables has a variance lower than variance of those variables. Any other questions? So then in terms of performance, there are a couple of examples in your textbook, and it's something like this. Interestingly, when we increase the number of trees, a kind of bagged collection of trees does not even overfit. So we can increase the number of trees as much as we want. We don't need to worry about it. So let's say this is some classification task. So this is sort of this would be the performance, the error rate that we're going to have with one decision tree. It is some value. And then if we use, let's say, 2 trees and aggregate them with the idea of bagging, we're going to reduce this error to some lower value. This is if we use 2 trees. But actually, with the idea of bagging, we want a large number of trees. Sometimes we would do n, because just with Bootstrap, it's common to get n Bootstrap samples so that we kind of shuffle the data sufficiently. Yeah?
If we have even number chain, which is a
Yeah. we need some tie-breaking rule in that situation. Whenever there's a tie, but this is just general in computer science, that in some situations when we are kind of making a decision, there's a tie, we should always think of a tie-breaking rule. And in general, tie-breaking rule is just a random rule. That says whenever there's a tie, just generate a random number, and based on value of that number being less than half or larger than half, decides between one of those candidates who were in a tie.
So it's better to set odd number.
Sorry?
So it's better to set
Yeah, that's one strategy that we pick this to be an odd number. But the thing is, it also depends, on the classification. If it is, whether it's binary classification or something else. But I mean, a tie could be also, between 3 numbers, right? Then you want this to be not a multiple of 3. All right. So here, if you use 2 trees and aggregate them, the error reduces. So this is, let's say, some test error. And yeah, as it turns out, this thing just decreases and kind of stabilizes. So this is some. This is the test error of a bagging, idea of bagging trees. This one here is essentially representing the error of a decision tree, just one tree, because number of trees is 1. So you can see that with aggregating a couple of trees, maybe we can have maybe hundreds of them, depending on how large the data set is. You can do hundreds or thousands. It's normal. And actually, this doesn't overfit. So you can do 5,000, not worrying that 5,000 is just an extreme value. It just stabilizes. It doesn't go up again. So this is bagging. And there's also a concept of there's also some sort of a free, let's say, cross-validated error. So I'm going to explain it. So we call it OOB. OOB represents out-of-bag measurement of the error. So the thing is here, when we did this Bootstrap sample, roughly 2/3 of the samples of the observations are here, right? You might remember there was a question in your midterm asking about this. 63%. So it's actually not 2/3. It's a bit less than 2/3. But just for the sake of argument, let's just say 2/3. So around 2/3 of these observations are here, and 1/3 of them are not in this bag. This is a bag. 1/3 of the observations are out of this bag. And this is a tree, right? Which is trained essentially based on those 2/3 of the observations. That's why that 1/3 of the observations are sort of a validation data set for this tree. So this idea of out-of-bag measurement of error is something similar to leave one out cross-validation. So both of them are very funny because these just look like 2 eyes. So out-of-bag and leave one out cross-validation were both kind of free measurements of test error that we can have. And that would be some measurement of how our model would perform on something it has not seen before. So technically, we can have this out-of-bag to represent, performance of this aggregated model, such that observations which are out of some bags are only evaluated and predicted using trees which were not grown based on them. So if you are systematic, keep track of which observations are not here, which of them are not here, and so on, we can reuse them to get some measurement of the test error without having a separate test data set. So this is going to give us out-of-bag measurement of the error for bagging. Also, leave one out cross-validation. It was sort of a free thing that we would get with cross-validation. Because so for none of these, we don't really need to follow the cross-validation process. We don't really need to separate things out, because for both of them, there are like mathematical formula that take the training set error and make some adjustments on them so that we can get some estimate of the test error directly from the training data set. So both of these are free. Computationally, they are free evaluations. Out-of-bag and leave one out cross-validation. Yeah?
Is there a reason why your out-of-bag error is lower than the test set error?
Yeah. So. Yeah. So but one of them is kind of, I would say one of them is giving us a better modeling here. So this is the case where we have a dedicated holdout data. We call it test data set. So this is about performance of a model trained on 80% of the original data set. But this is about performance of a model trained on 100% of the data set without having any holdout data. Yeah. So here, the accessible data is 80% or so, because before doing anything, we're going to separate some holdout data and don't use it at all. That's why our model will not become the model that we would have from using all of the data. So these two don't have to be different. In this case, and in the example of your textbook, they are different because n was not such a large number. So let me just explain it again. This is our data set with the idea of the separate holdout data. We're going to say this part is holdout, so we can only have access to 80% of the data. And this 80% will be then bootstrapped, and then these trees will be trained on 2/3 of the 80%. So they just have less information to be trained. But with the idea of this sort of free evaluation, the accessible data set is 100%, and the trees are trained on 2/3 of this 100%. So they just become better trees. But in situations where n is relatively large, 80% of something huge, and all of it is not that different, then these two will be the stabilized evaluation of the same thing, essentially. All right, let's take another quick break, and then we discuss random forests.